This video includes information on the periodic table. First, let's look at some historical information. So Mendeleev and Meyer independently recognized that there are periodic relationships between the properties of elements. Now, Mendeleev took that one step further. He actually used the information he knew about known elements to predict the existence of unknown elements and the properties of those unknown elements. When gallium and germanium were discovered, the properties of those elements very closely matched the predictions that Mendeleev had made, and therefore provided great support for Mendeleev's work. And this is just a kind of picture of what an early Mendeleev periodic table looked like. Now, when we look at the periodic table, there are some things that we need to know generally first. So each element is represented by a chemical symbol. The chemical symbol is a 1 or 2 letter symbol for that particular element. Going across the periodic table horizontally are what we call periods. And going down the periodic table in each column is called a group. And elements that are in the same group have very similar chemical properties. Now, when we look at the periodic table, we can generally classify substances that are on the left-hand side of the periodic table as metals, elements that are on the right-hand side of the periodic table as nonmetals, and elements in the middle as what we refer to as metalloids. They have characteristics of both metals and nonmetals and are kind of the dividing point between our metals and our nonmetals. Now, we've got some group names that we should be familiar with. So when we look at our metals, the elements that are in the first group are called alkali metals. In the second group are called alkaline earth metals. And in this middle section here, we refer to them as transition metals. Now, over on the right-hand side, we have pnictogens, which is not a very common term at all. Chalcogens, which is also not very common. And then here, one group over from the right are halogens. And then the last column all the way over on the right are what we refer to as our noble gases. Now, down along the bottom of the periodic table, there are 2 extensions of the periods, which are pulled out of the main periodic table and put down on the bottom. They're called the lanthanides and the actinides. Now, a key to understanding periodic trends has to do with what's called Coulomb's law. And Coulomb's law has to do with the attractive force between unlike charges. So in this particular equation, the Q plus is the charge on the nucleus, and it's positive because the nucleus contains protons and neutrons. Q minus is our electric charge, so that would be the number of electrons that would be found outside the nucleus. And then d squared deals with the distance between those 2 charged particles. So we should see that the force of attraction is directly proportional to the product of the charges for the nucleus and the electrons divided by the distance between the nucleus and the electrons. So when we talk about our principal quantum number, we should remember that the symbol we use is N. And as the principal quantum number increases, that means we have more and more energy levels, the size of the orbitals increase, and the electrons spend more time farther away from the nucleus. So if we were to look at this model here, we've got our positive nucleus here, which contains the protons and the neutrons. And then we have this electron of interest here. Now, the electrons that are found outside the electron of interest are going to have no effect on the pull that this electron would have towards the nucleus. But the electrons in between the positive nucleus and the negative electron of interest will affect the attractive force between the two. We call this shielding. So we've got the positive nucleus and the negative electrons, and we know that positives and negatives are attracted to each other. But the more electrons we have between the positive nucleus and the negative electrons, it's going to decrease the attractive force this electron feels. And we would call that the effective charge. So electrons closer to the nucleus slightly repel outer electrons, offsetting their nuclear attraction. Now we're going to talk about covalent radius. And by definition, it's 1/2 the distance between the nuclei of two identical atoms when they're held together by a covalent bond. So, as an example, if we were to look at two fluorine atoms that are being held together by a covalent bond, if we measure the distance between their two nuclei and divide that by 2, that would give us our covalent radius. Or if we have two chlorine atoms that are covalently bonded together and we measure the different distance between the two nuclei, half that distance would be our covalent radius. Now, there is a trend on the periodic table with respect to covalent radius. As we go down a column, down a group on the periodic table, the covalent radius increases. And the reason for that is as we increase n, our principal quantum number, we're adding more and more energy levels, and the electrons are going to be farther and farther away from the nucleus. Now, we also have a trend for covalent radius going across a period. As we go across a period on the periodic table, the covalent radius decreases. Now, the reason for that is as we move across the period on a periodic table, we're adding more and more protons to the nucleus and more electrons outside the nucleus. So our Q1 and Q2 are going to be increasing. The force of attraction will increase, and the electrons actually get drawn closer into the nucleus, decreasing the radius. So atoms that are to the left and the bottom will be bigger. Atoms to the right and towards the top will be smaller. Now let's look at atomic radius graphically. Okay, as we go down a group, we're going to notice that the atomic radius increases. So we've got lithium, sodium, potassium, and rubidium. Those are all alkali metals, and we see the trend for increasing atomic radius. Now, as we go across a period, the atomic radius decreases. So if we were to look here from lithium through neon, we see a decrease in atomic radius. Or from sodium to argon, we have a decrease in atomic radius as we go across the period on a periodic table. Now, when we deal with anions are negatively charged ions. They're formed when atoms gain electrons. And when we have more electrons, we'll have greater repulsion among those electrons that will decrease the effective charge per electron. And those electrons will spread out. So the atomic or the ionic radius of the ion will be larger than the atomic radius of the atom it was formed from. When we talk about cations lose electrons and form positive ions. And when they lose electrons, that's going to make the attractive force greater, and it's going to pull the electrons in closer. So the ionic radius of a cation will be smaller than the atomic radius of the atom it was formed from. Now we have this term isoelectronic. The prefix iso means the same. So when we deal with isoelectronic series, they are atoms and ions that have the same electron configuration. It literally means isoelectronic, same number of electrons. So as an example, if we have a nitride ion with a -3 charge and an oxide ion with a -2 charge and a fluoride ion with a -1 charge, and then neon, a sodium atom, a magnesium atom, and an aluminum atom, they all have 10 electrons. So they're all considered to be isoelectronic. Now let's look at their sizes. We'll look at the atom's size first. So an oxygen atom has a atomic radius of 73, fluorine is 71. That makes sense because the atomic radius typically decreases as we go across a period. Now, if we were to look at sodium and magnesium and aluminum, again, we're seeing that the atomic radius is decreasing as we go across that period. Now let's look at the ions. Okay, we've got an oxide ion, a fluoride ion, a sodium ion, a magnesium ion, and an aluminum ion. They all have 10 electrons outside their nucleus. The difference is how many protons they have inside their nucleus. The more protons inside the nucleus, the greater the attractive force for the electrons, and the smaller the size will be. So if we were to look here, again, this is what we would refer to as an isoelectronic series because all of these ions are isoelectronic to argon and have an electron configuration of neon, 3s2, 3p6. So which of the following atoms and ions is or are isoelectronic to sulfide? So what you want to do is you want to figure out how many electrons there are in a sulfide ion, and then figure out how many electrons there would be in each of these examples, and you're going to match up which would be isoelectronic. So sulfide, we find sulfur here has 16 electrons. A -2 charge means it's gained 2 electrons, so it has 18 electrons. Now, if we were to look at silicon with a +4 charge, it has 14 protons in the nucleus and 10 electrons outside the nucleus. That's not isoelectronic because it doesn't have 18 electrons. Chlorine has 17 electrons, or 17 protons, and if it's a -1 charge, it has 18 electrons. That would be isoelectronic to a sulfide ion. Argon has 18 protons and it's neutral, so it has 18 electrons. It would be isoelectronic to sulfide. Arsenic, if we look on the periodic table, has 33 protons and 33 electrons because it's neutral. The number of electrons don't equal the number of electrons in sulfide, so it's not isoelectronic. A potassium ion has 19 protons and it lost an electron, so it's got 18 electrons. That would be isoelectronic. And a magnesium ion has 12 protons. It lost 2 electrons, so it has 10 electrons. It would not be isoelectronic. So we would have chloride, argon, and potassium as being isoelectronic to sulfide. Next, we want to talk about ionization energy. And essentially, ionization energy is the amount of energy that's required to remove an electron from a gaseous atom or ion. Our first ionization energy is the energy required to remove an electron from an atom. So we've got our atom here. There's an attractive force between the positive nucleus and the electrons. So in order to remove an electron, we're going to have to add energy in. That's our ionization energy. The first ionization energy for an element is the energy required to form a cation with a +1 charge. Now, the energy required to remove the second electron is called our second ionization energy. And if we were to remove a third electron, it would be our third ionization energy, and so forth. Now, there's a trend for ionization energy on the periodic table. As we go across a period, generally speaking, the ionization energy increases. And as we go down a group, the ionization energy decreases. But there are some exceptions. If we were to look at beryllium here, it has an ionization energy of 900 kilojoules per mole. Boron, we would expect to be higher based on the trend, but it's actually a little bit lower. The reason for that is beryllium is, when we look at its electron configuration, 2s2. Its s orbital is filled. When we go to boron, we're adding an electron to the p orbital, and it takes a little bit less energy to remove that electron from the p orbital than it did to remove an electron from that 2s orbital. Now, another thing we might see as we go across, generally speaking, that ionization energy is increasing. But again, we're going to see a discrepancy here between group 15 and group 16. And the reason for that is, if we think about all the elements that are in group 15, their electron configuration is such that their p orbital has one electron in each of the orbitals. If we go to group 16, we're adding another electron in. So as an example, this is the orbital notation for oxygen. Here's that extra electron here. It's going to require less energy to remove this electron from oxygen because we have paired electrons in this orbital. Require less energy for that electron to be removed. So let's compare successive ionization energies. So here, this is the energy to remove the first electron from a gaseous atom. This is our second ionization energy. So we'd be removing an electron from a cation with a +1 charge. This is our third ionization energy. We'd be removing an electron from an ion that has a +2 charge, and so forth and so on. So what we should notice for potassium, the first ionization energy is less than the second ionization energy. And that will always hold true, because if we're removing an electron from a neutral atom, it's going to require less energy than if we're removing an electron from an ion with a +1 charge. Now, there's a pretty big gap between the first ionization energy and the second ionization energy for potassium, because here we're removing what we call our valence electron, but here we're starting to remove core electrons. And it takes more energy to remove core electrons than it does to remove valence electrons. So calcium has 2 valence electrons. So this is the energy to remove the first electron. This is the energy required to remove the second electron. And again, notice there's going to be a big jump from the second ionization energy to the third ionization energy. And that's because we're removing valence electrons here, but now we're removing core electrons. So scandium has 3 valence electrons. So here's our first ionization energy. We're removing our first electron. Here's our second ionization energy. We're removing our second electron. Here's our third ionization energy. We're removing our third electron. And then the big jump is from valence electrons to core electrons. So we can figure out how many valence electrons are in a particular atom by looking at what their successive ionizations are. Now let's talk about electron affinity. And electron affinity, which we're going to shorthand as EA, is the energy change that takes place when an electron is added to a gaseous atom to form an anion or a negative ion. And generally speaking, the absolute value of our electron affinity increases as the atoms get smaller. So that means as we go towards the top and towards the right, our absolute value of our electron affinity will be increasing. But again, we're going to have some exceptions. Okay, going past a filled sublevel is not favorable, so there's a difference between beryllium and boron. And pairing electrons is unfavorable, so we've got a difference between group 15 elements and group 16 elements. Now, if we look, most of the values are negative values, and that's because energy is being released as the electron is being added in to form an ion. Here are some questions to practice. It says, predict which of the following would have the largest atomic radius. So remember that atomic radius is larger as we go to the left and as we go towards the bottom. So the largest one would be the farthest to the left and farthest to the bottom. That would be rubidium. Then, which has the lowest first ionization energy? And the first ionization energy is going to be decreasing as we go towards the left and decreasing as we go towards the bottom. So if we want the lowest one, we want the one farthest to the left and farthest to the bottom. And that would be barium. And then for the last one, it says rank the following by increasing first ionization energy. That means we want the one with the smallest first ionization energy listed first, and the one with the largest first ionization energy last. Remember that our ionization energy decreases as we go to the left and the bottom. So the smallest ones will be over here. And it increases as we go to the right and towards the top. So the largest ones would be over here. So we would have magnesium, silicon, sulfur, and oxygen. Now, understanding these trends is going to make it easier for us to deal with chemical reactivity. So as an example, chlorine has a high ionization energy and a very favorable electron affinity. That means that chlorine atoms tend to gain electrons and form chloride ions. If we were to look at sodium, sodium has a very low ionization energy and an unfavorable electron affinity. That means that sodium tends to lose electrons and form cations. So we're going to start to see a relationship between things like chlorine and sodium. Chlorine wants to gain electrons, sodium wants to lose electrons, and we're going to see that there's a relationship between sodium and chlorine because we'll have a transfer of electrons from sodium to chlorine.